Welcome to the 6th month of AOA. We'll be going over applications of graph theory and more algorithms that we use on graphs. Here's an overview of what we'll be covering. Feel free to pause here. The first thing that we'll be going over is breadth first search, or BFS. Last month, we covered depth first search, so now we'll be covering breadth first search, which is a different way of traversing a graph. How BFS works is it chooses an arbitrary node and then it goes through its neighbors, so it goes in layers rather than going as far as possible. You can see in this animation how BFS works compared to DFS. The difference between these two algorithms is that depth first search uses a stack, so that way it goes as deep as possible, while breadth first search uses a queue. First, it visits all of the neighbors' nodes, then it goes to the first neighbor, checks its neighbors, and once all of those have been visited, it moves on to the next neighbor of the original node. This process is repeated until all of the nodes have been visited. The reason why breadth first search is really useful is because we can use it to find the shortest path in a given graph. So first, we'll use BFS starting from a given node that we choose as our origin. We store these nodes that are already visited from the BFS algorithm in some sort of array, and once we reach the destination, we return the shortest path that was taken. The reason why this works is because BFS works in layers, so as soon as the destination node is reached, we know that that is the shortest path possible. However, this algorithm only works on an unweighted graph that has no loops. Once we get into real world, where graph theory will obviously imply edges with weights, we'll need more advanced algorithms. The first of which is Dijkstra's algorithm. A fun fact about Dijkstra's algorithm was that it was created by the Dutch computer scientist Edgar Dijkstra in just 20 minutes when he was having coffee at a cafe. Something to know about Dijkstra's algorithm is that it's a greedy algorithm, which means that it makes the best, most optimal, and most logical choice at each given stage. Because of this, it only works on a graph that has positive edge weights, which means that if the graph has negative edge weights, it won't necessarily return the most optimal paths, and I'll explain why later. The first component of Dijkstra's algorithm is that it creates a table of nodes and their distances. The starting node has a weight of 0, which makes sense because it takes 0 distance to go from the starting node to the starting node. All of the other nodes temporarily have a weight of infinity because we don't know how far it is to get to that node. Dijkstra's algorithm will run breadth first search and checks to see if the total distance is less than its current value. If it is, then it will be replaced with a smaller value. An example of this in real life is if I want to get to school, I'm going to assume that it takes maybe 100 miles to get to school. Once I find a path that only takes 10 miles, I can update that and then say that it only takes 10 miles. Then if I find a path that's even better, that's say maybe 5 miles, then I can re-update and say that it takes 5 miles to get to school. This algorithm is completed once all of the nodes have been visited and assigned values, and all of the distances have been optimized. Now, what if the graph that we're looking at has negative edge weights? The reason why Dijkstra's algorithm won't work is because maybe taking a certain path that might seem optimal at a certain location is not actually the most optimal path overall. Because if there's, say, a negative edge weight lurking around somewhere that never gets reached, the most optimal path won't necessarily be taken. And that's why we sometimes use the Bellman-Ford algorithm. It's a little bit slower, but in exchange for the extra computational time and comparisons, is able to work with negative edge weights. Much like Dijkstra's algorithm, it creates a table of nodes and distances, and then it traverses through all of these nodes and records the distance between each combination. This is really important for the next step that's known as relaxation. Relaxation will compare these different distances and choose the one that's the most optimal. So that means that if it traverses a negative edge weight, that will be prioritized. This algorithm will continue running until the shortest path is constructed from the start node to all of the nodes possible.
Great, and now to start discussion of the minimum spanning tree. So the minimum spanning tree is a collection of edges that connects every single vertex in a given tree with the lowest total combined weight. So while you might not reach each individual vertex in the most efficient manner that takes the least weight, it means that to reach all of them, this is the most efficient way. So there are many different algorithms that we'll talk about that find the minimum spanning tree, but all of them result in a tree with the least total combined weight through adding up all the edges. So some possible applications of the minimum spanning tree, including, for example, setting up different gas stop locations where you want the total combined distance between each gas station to be as low as possible to ensure that people don't run out of gas in the middle of nowhere. Likewise, if you want to build centralized transportation infrastructure, you want to be able to reach as many places as possible while using the least amount of total track or whatever other construction material you're talking about in order to minimize the total cost. For this reason, we often want to find the minimum spanning tree, and there are many different ways to do it. One way to do it is to use Prim's algorithm, which, like Andy mentioned earlier, is a type of greedy algorithm. So that means it'll always make the greediest, or the choice that requires the least amount of weight in this case, at any given steps. The steps for Prim's algorithm specifically are to first set every non-starting vertex's weight to infinity, or travel distance. Then, going from the initial node, gradually update each additional node visited based on the lowest weights available. For example, in the picture below, if we started at 0, 1 and 7 would both have weights initially of infinity. But as the distance from 0 to 1 is 4, which is lower than infinity, the weight of 1 gets updated to 4. Likewise, with 0 and 7, the weight of 7 gets updated to 8. This continues so on until you find the minimum spanning tree. And the reason that this works is because we're always updating nodes whenever we see them. For example, the way to get from 0 to 7 to 8 to 2 is less efficient than from 0 to 1 to 2. And if we reach 2 first, going from 0 to 7 to 8 first, we'd update it once we reached 0, 1, then 2, ensuring that all the possible weights are the lowest values that they can be. Another way to find the minimum spanning tree is with Kruskal's algorithm. Now, this works a little bit differently and it's slightly more advanced. The first step is to sort all the edges in a non-decreasing order of their weight. This means that there are multiple possible sorts, but the only requirement is that the sort must have edges in a non-increasing order. Then we'll first select the smallest edge. We'll see if this forms a cycle with the tree so far, and if it doesn't, then we'll include this edge. Otherwise, if it does, it means we've already been here and we'll discard it. We'll repeat step number 2, which is the previous step for checking for a cycle, until there are v minus 1 edges in the spanning tree. That's because once there are v minus 1 edges, then you can be sure that you've connected all v nodes. This then returns the minimum spanning tree of the given graph. Finally, we'll be talking about bipartite graphs. So the bipartite formal definition is a bit of a mouthful, but it essentially means that you can divide every vertex in your graph into two different distinct subsets, such that no two vertexes from the same subset are touching. So, for example, in the picture below, you can divide every single vertex into either a letter or a number, and none of the letters touch each other, while none of the letters touch each other. And this is useful to consider because there are real world relationships that we want to know if they're able to be divided bipartite. For example, if we have job openings and we have a certain number of applicants, we want to be able to match each job opening to an applicant, but we don't want to be able to match, like, for example, applicants to other applicants or jobs to other jobs, because that wouldn't make sense. So some really easy ways to detect if a graph is bipartite is to use either BFS or DFS and assign a value to each graph. Now, this value can change between either odd or even, and if a value is odd, you want to ensure that there are no cycles, meaning that it's not touching any, or it's not adjacent to any other odd numbers. And if a value is even, then you want to make sure it's not adjacent to any other even numbers. And that concludes our video for today. Stay tuned next time as we report month 7 of AOA.